Good morning, everyone. Um, in the e-learn, uh, I have put two pre-labs and lab problems that I've recently done on campus to give you a flavor of what kind of problems we do in the lab. Uh, Even on campus, I do not have regular labs. So these are the extra labs that I conduct so that students get a hands-on on these. So these pre-labs are for OpenMP and MPI. So there is a pre-lab document which tells students what is expected, and then the lab problem. Both of them are uploaded on the e-learn. You all can try those out. Uh, it's your choice. There is no grading or anything on it. So let us begin today's class. I hope I'm audible. I hope the screen is visible.
Yes, ma'am.
Yeah, thank you. Okay. So in today's class, we will start with the food module, that is scale out and redundancy. So what is scale out? See, as applications grow in size and complexity, the amount of data that we need to store, process, and transfer also increases. So traditional centralized designs that we've seen so far, they often cannot keep up this with this growth. So we need these scale out architectures, which are where we can add more nodes horizontally instead of just increasing the power of the existing ones. So with this, what happens is we have a way to build systems that are more flexible and that are capable of handling growth and increase in the size of data to be processed. So why do we need to scale out? It's because we've seen the master slave architectures in earlier classes as well. The master slave architecture is simple but effective for small scale systems. But as our cluster grows to hundreds or thousands of nodes, there can be several challenges which will emerge. Okay? So the first could be that if there is a bottleneck at the master node, because all coordination, scheduling, metadata management, decision making, everything passes through a single node. As there is an increase in this workload and number of requests grow, the master node may become a performance bottleneck. So, for example, if a master node is handling 10 workers, it's fine. But what if it's asked to take care of or manage 1,000 workers or 10,000 workers? The next issue with master slave architecture is scalability. The master node hardware can have physical limits. It will have some CPU, memory, input output limits. So once those limits are reached, adding more worker nodes cannot improve the throughput because the master node is not capable of keeping up with this expected demand. It also has to take care of the state and heartbeats of all the workers. It should check if the worker is working, if there is an issue with the worker. So the more workers you add, the more time is spent on this coordination overhead. That is, basically communication and bookkeeping of each of the worker. Master node also becomes a single point of failure because if the master node fails, the entire system will halt. Even if all worker nodes are healthy and available, once the master node fails, the system is halted. Another limitation is the fault tolerance. When with master slave systems, We require complex failover strategies. Like we have to take a back of the master. We have to then do the leader election, choose a new master if you want to, recover from these failures. And this is not easy as it sounds. This adds complexity, also adds extra overhead and delay in the performance of your system. Masternode also has a centralized metadata management issue. So when we have a metadata, by metadata what I mean is file, location, what are the tasks which are assigned. So these metadata is stored centrally. The size and access time grows when you have more and more worker nodes connected. So this will eventually slow everything down because the metadata is centrally managed. For example, so if we have a in a classroom environment, we have a teacher who has to individually assign and review, assignments for 1,000 students. Eventually, the teacher will be like may become the bottleneck because it regardless of how good the students are, the teacher may need much more support in order to take care of this task and may not be capable of helping out 1,000 students for a particular assignment. So out of the problems we've discussed, the single point of failure and bottleneck is perhaps the most critical because why it is critical? All communication paths will go through the master. Any network glitch, software bug, or hardware failure will stop the system. Even if we have a backup for a master, switching over can lead to downtime and also lead to inconsistency. So, since the large scale distributed system must run 24 by 7, a design that depends on one node for coordination or metadata management is not good enough. It cannot offer fault tolerance. We'll to see two case studies. The first one is Google File System. In Google File System, there is a centralized master model. One master node keeps, the metadata, which is namespace, file to chunk mapping. Even the even who are allowed to access these files, while many chunk servers store the actual data. So chunk servers are connected and they are expected to store this chunks of data. The advantage of this is its simplicity. Global knowledge of the system is available at centralized master node very fast. Easy metadata consistency. There are no multiple copies of the master node has the metadata details, but there are limitations as well of the system. Master can become a bottleneck if there are many metadata requests. How the Google file system works is there is replication. To have another system which has all the you know data that the master node has and also with all the records that the master node has. In case of failure, we have the data replicated. But despite this replication, if master node fails, it will lead to significant performance degradation. Again, scaling beyond a certain point will require complex mechanism. That is, we will need shadow masters log, we need log replication, which is obviously it has to be done. Otherwise, the system, yeah, we will this system will not be useful if the master name fails. So that is taken care. The other option that we have, or what we are going to learn in today's class, is the P2P model, that is peer-to-peer architecture, which is implemented in BitTorrent. In BitTorrent, there is no single master. Peers provide and consume data. So basically, BitTorrent shows how a decentralized architecture can achieve scalability and fault tolerance that the centralized, master slave architecture struggle to match. So what do we get through this? Is master slave architectures are easy to build, and they are, and we can scale them gracefully without, and we are not bound by a certain size. The centralized coordination creates bottlenecks and single point of failures, which we overcome through this P2P decentralized approach distributes this data, the control as well as data. It gives you, scaling capability, self-organization, and even robust, fault tolerance. So how it works is each peer, which part of this decentralized P2P model, they know each other and exchange data directly. The metadata, the torrent file, is distributed. Peers download and upload simultaneously, and this data is also get distributed. Advantage: we do not have a single point of failure. System continues even if many peers come and leave. It automatically balances the load, and we've seen it scales to millions of peers as well. So now let us learn what is this peer-to-peer architecture. So the peer-to-peer architecture is where there is no central master node which controls everything. Instead, we have all nodes, which we call peers, are equal participants. Every peer can act both as a client and a server. So, can you think of examples where your laptop might be both a client and a server?
In in case of torrent, once I download something uh, and someone
Yeah.
wants to download it again, my laptop become the server for the peer.
Hmm. Hmm. Yes. Yes. In torrent, yes. Any other example? Think of remote access to the desktop, where you enable remote desktop access on your laptop and allow other devices to connect to it remotely. Whereas you also use remote access to on the same laptop to connect to another device or to test the remote access setup. So it could be any, or you can also, set up a local database where, as in server role, you are running a local database, MySQL, on your laptop for some development or testing purpose. In the client role, you will use this database on the same laptop to interact with the database, sending queries and receiving results. So basically, what you do is you request data or services from the others, and it can also provide data or services to others. So this P2P architecture, This collaborative model changes the dynamics completely from what we've seen in the master node setup. Because there is no single master coordinating everything, we also eliminate the problem of a single point of failure. So if one node goes down, the system continues to function because others can take over its responsibility. So another big advantage here is scalability. In a master-slave system, adding more workers eventually overloads the master. But in a P2P system, adding more peers actually increases the system's overall capacity. We get more storage, we get more bandwidth, and we get more compute as well. So we can say that P2P networks are naturally robust and fault tolerant. Nodes can join and leave anytime, and the system will adapt. That's why this paradigm is the foundation of many large-scale distributed file systems, which can include systems from like file sharing networks like BitTorrent to any kind of distributed database or even blockchain platforms are part of this P2P architecture. So visually, we can say that P2P architecture looks something like this. So earlier we had master slave architecture, client server architecture, which there is a server and there are multiple clients. Whereas in P2P architecture, everyone is a master as well as a client, and they all are connected to each other. Is the architecture clear? How it is different from master slave? Okay. So now that yes, someone is saying something. Okay. Now that we have seen what a P2P system is, let's talk about what are its characteristics. The thing that makes it different from the traditional centralized system. First, the P2P systems are decentralized. There is no central control or master node. Each peer is autonomous and can make its own decisions. And this is what makes this system, different, and it helps you to remove the bottlenecks and single point of failures, which we have discussed earlier. Second, they are symmetric. Every node plays the same role. It can both request and provide services. So instead of having specialized servers and passive clients, we have a network of equal peers. The third, they support dynamic membership. Nodes can join or leave the system at any time, and the network reorganizes itself to maintain this connectivity and functionality. This helps you. This is very critical because in large scale real world systems where nodes are constantly changing, this is a very critical characteristic. Fourth, the scalability is built in because every new peer contributes resources like storage, processing power, or bandwidth. The overall capacity of the system grows as the network grows. And this is very different from a centralized system where adding more clients often can lead to increase in the load of on the server. The fifth one is P2Ps are naturally fault tolerant. If a node fails or disconnects, others can step in to provide the same data or services. The system keeps working without a central coordinator having to fix anything. The final one is obviously with this setup, they enable resource sharing. Each peer contributes some part of its resource like files, bandwidth, or even computation. And this benefits from what others share. So this collective behavior is what makes the systems like BitTorrent that we see so efficient. Together with all these characteristics, the P2P systems are more resilient, adaptive, and scalable, which is why they are used in so many distributed applications. So we'll now see different types of P2P networks and what are the real world, you know, examples of these type of P2P systems. So P2P systems can be divided roughly in these types: pure P2P networks, hybrid P2P networks, overlay P2P networks, structured P2P networks, and unstructured P2P networks. So the first one being a pure P2P network, which are the most decentralized form of peer-to-peer architecture. There is no central authority here. Every node in the network is equal. Each peer both request and provide resources, and communication happens directly between the peers. Because there is no centralized component, these networks are highly resilient and scalable. Even if many peers leave or fail, the system continues to operate. However, the downside is that the task like searching for a resource or managing the network can become a bit less efficient as system grows. So some of the best known examples of P2P are pure P2P are BitTorrent and Tutela, which which rely entirely on peer to share the data and keep the network running. We can also have hybrid P2P network. So what do we mean by hybrid? Is P2P networks, hybrid P2P networks try to strike a balance between decentralization as well as efficiency. They keep the peer-to-peer communication model but add some central components like servers or a set of super peers. Now, the super peers try to coordinate certain tasks. So, these super peers might help manage indexing, handle queries more efficiently, or even relay messages when direct peer-to-peer connections are not possible. The goal to have this is to overcome the inefficiencies of pure P2P systems like slow searches and all, but you know, while retaining scalability and fault tolerance or reducing it. So anyone can summarize uh, or can tell why we need a hybrid P2P network and why a pure P2P network will not work. Pure P2P network works, but why hybrid is better than pure P2P. The reason is I already mentioned if you have a pure P2P network, you have to search. If you're trying to search something, you might have to search on every node possible, right? The data. If you do, if the metadata is not with a single node, it is with every node. Then, if you want to search for something and searching that metadata, you might end up searching in every node's metadata, which is time consuming. Whereas in a hybrid P2P, now these are the servers if they have the metadata for their particular, you know, cluster, then in this case we will be searching in only six systems. That's why, especially for such tasks like searching, the hybrid P2P networks work better because it along with it has both, the advantage of a classic master slave architecture as well as P2P network. So it overcomes the limitation of classical master node because it does not have only one single master node, but it also overcomes the limitation of a P2P, which has pure P2P, which where searching might take or degrade performance.
Ma'am, can you go to the previous slide?
Yes.
How this fault tolerance is going to work here? Because if for one servers, uh, it's a kind of single point of failures for one server. If master is down, then what is going to happen to the connected peer?
So here in this case, in this case, only four of them will get affected, right?
Yes.
Okay. But rest of the system can continue. Only one part or of the system or a few nodes will get affected. Then you will replace the master, do the election. That will happen.
Okay. Okay.
But if this system, instead of this system, you have only one master which is correct in all 16, 17 systems,
Hmm.
then that becomes a single point failure
Yeah.
for 16, 17 systems.
So there is a mechanism to hand over if there is one master getting down,
Yeah.
connected peer from that master to get some other master connected
Yes.
to those.
Then they will do a re-election between
Okay.
those peers. Choose a master node, then that master node will take over.
Okay. Okay.
Okay. But this process will take a certain amount of time, which will add the overhead, but that is only for a few nodes.
Yes.
Okay.
Yeah, ma'am,
Thank
in pure,
Yeah,
pure, peer to peer, the earlier slide.
yeah,
Here, each peer is connected to all other peers. So any new addition or removal of peer is going to be complicated that way, right? It will need to make a connection with all the remaining peers in order to get functional. Wouldn't that be
yes.
costly affair?
It will, it, yes, it will be a bit costly. Will be a bit costly, but it's more reliable than master node architecture and scales also scalability wise. You
Okay,
can keep
and
adding nodes.
right, but
Yeah,
whenever a new node gets added into the network, it will need to tell other peer nodes that I'm there, I'm there. So that
yes,
whenever a request is there, the other peer will have other peers will have information to reach to that particular new node and they can fetch the information from it, right?
yes. So, yeah, you're saying something?
Yeah,
You
another
know,
thing is each peer in this particular setup has all the information or it has part of the information.
so it will have part of the information. That's why we have to search on multiple nodes.
Okay, so request could be taken up by any peer and then
Mhm.
if he tries to see if I have the information. If no, then he will go to rest all peers to figure out who has that information in a way, right?
Yes.
Okay.
So P2P systems have advantages like decentralization, resource sharing, but they also come with challenges in terms of management, data consistency, even security, as well as the scalability challenges that you mentioned compared to the master slave architecture. But at the same time, they also provide you some advantages over master slave, such as single point of failure and other that we have seen over master slave. So both systems have their advantages and disadvantages, and depending on what is your what is your priority, you'll have to choose the architecture.
Yep.
Yeah. So an example of hybrid P2P will be a Skype or eDonkey or early Nextstep architecture. Then you have a overlay P2P network. So overlay is where you add an extra layer of abstraction where you create virtual network on top of the physical internet. So in this, what you do is peers are connected through logical links that that may not be exactly how they are physically linked. Okay, so as you can see here in an internet, in this figure, these different nodes have formed a logical link, right? Which may not be exactly how they're physically linked. So here there are three systems, here there are two systems, here there is one, here there is two, but they form one logical link for each of them and they are connected. So this helps peers to organize themselves in ways that makes the routing and resource discovery much more easier. So most of the P2P systems use, distributed hash tables or DHT to quickly locate which peer has, the particular resource. So this can include CORD and Cademia, which are well-known DHT-based overlay networks. So the advantage of these networks is it makes it possible to find any data in of login steps, even if you have like millions of peers. So, so you basically create a virtual network over the physical network and do the using hash table find the other nodes. Then we have two more types of P2P networks, which are structured and versus unstructured.
Yeah, ma'am, one question on earlier slide.
Yes.
What is distributed hash table?
So when you are trying to, we will talk about hashing in the next slide. But when you are trying to find a node for reading storing data, in that case you have to locate this node, right? So how do you locate this node? Is you have a hash key for each of the file that you are trying to store in a particular node. With this hash key, you when you calculate the value, you get the node value on which this data should be stored. So how it helps
Okay.
you to decide where your data will be stored or from where your data will be fetched.
Okay. So, um,
Yeah.
how that
So
hash would be computed based on a file though?
yes. So a hash functions will take the input data, that is a file name or node identifier, and it will generate a fixed hash key. Okay, and this
Mm-hmm.
key is used to determine the location of this data or node within this overlay network. So let's say when a data is added to the network, it should be first hashed to generate this unique key. Now this
Mm-hmm.
key will
Mm-hmm.
determine where this data will be stored or replicated within this network. for
Okay.
storing the data or storing a file. Now, for node identification, nodes in this overlay network are also identified using hash keys, which tells you how to route and locate the data.
Okay.
So,
Assuming a situation. Okay.
yeah.
Assuming a situation wherein we kind of compute a hash key, keep a data on a certain node.
Hmm,
Let's say after some time there is a read request for the same data.
hmm,
As in, let's say we store a
hmm,
file on node A, for example, which is part of the part of this
hmm,
particular setup. We compute the hash key. We know that A is the node which needs to
hmm,
or who needs to hold this particular file, and we store the file on node A, and
hmm,
then node A goes down, and we get
hmm,
a request to read the same file which is stored on node A. So we compute a hash key. We'll know that A node is something where this information is expected to be present, but A node
hmm,
is not there anymore, right? How
hmm,
those
hmm.
kind of situation will be tackled?
Uh, okay. Um, yes, that's a good question. So you calculate the hash key and you find out that this node is missing. In that
Correct.
case, you will need, first of all, redundancy. You have to ensure that the data is replicated across multiple nodes to prevent such loss or case of failure. You can, also use, you also have an option of using a hash ring where if a node fails, the hash ring will update and redistribute the data to other nodes. Okay, we'll see how that is done. We have
Okay.
one example
Mhm.
in the later slide.
Okay.
Um, so we will also have to have some data recovery mechanism, which will restore the data from the failed nodes and whenever there is issue. So kind of a backup system. So
Okay. So
uh,
for
yeah,
every node which is participating over here, we'll need to have some replica mechanism, is what you're trying to come at. So if that
yes,
node goes
yes,
down, there is someone else who also had similar data. So request could
yeah.
be routed to the other node in case it is
So
not
there
available
could,
at this.
yeah. So in case a node fails, you might have to remove that node, add a new node, and redistribute the data accordingly.
Okay. And as far as storage is concerned, as in that particular
Yeah.
node's storage is going to be used for storage purpose that way. There isn't anything called central storage kind of a thing. Every node is
No.
going to bring his storage in the gameplay,
Yes.
and
Yes.
he is going to store the file actually.
Yeah. The BitTorrent example that we saw. So,
Okay, and then distributed hash table, is it actually a table which stores some information, or it is just notion which gets computed on the fly?
this distributed hash system, you will is a uh, distributed hash table is what it is called. It needs to be stored because it will have the hash keys to map data to nodes in a P2P network.
Right, but if it is a table and if it is stored at some place, and if that node itself goes down, then we don't have a mechanism to identify which particular node I should send the request to. Wouldn't that be a single point of failure?
See, in DHT, the data is not stored in the central location. It is
Okay,
distributed across multiple nodes. So
okay.
each node in the network will store a portion of overall data. And this again, this data is mapped to nodes using the hash function. So each node is responsible for a specific range of hash keys and stores the data associated with those keys.
Right, but the question which I'm trying to ask is a certain node is going to serve certain hash keys, right? So basically,
Mm-hmm.
if there are 100 nodes in the system, I there needs to be a mechanism to tell that first node is serving, let's say, from 1 to 10 hash keys. Second node is
Yes,
from 11 to 20, something of that sort, right? So is
Yeah,
that
yeah.
information stored in some table, or there is some
So
centralized
that
place wherein that information is held up? Something of that sort, I'm asking.
yes. So DHT, the distributed hash table, is the one who is responsible to have this, hash and
Hmm,
the
hmm.
file details. Okay, and uh, okay. So let me yeah let me start from the beginning. The hash function will map the data to a unique identifier, right? Then
Correct.
each node in the DHT is assigned a unique identifier within that same hash space.
Mm-hmm.
Okay. Then this hash space is divided amongst nodes, with each node responsible for a specific range of hash values.
Correct.
Hmm. So
Correct.
when you're trying to add a data to this DHT, it is hashed to generate this unique key. Then this key is used to determine which node is responsible for storing data, and then this data gets stored on that node. Okay.
Okay.
So for that, you use a DHT algorithm, which will, depending on what kind of mapping is done for this. Like for a chord, it uses a ring structure to map nodes to hash keys. Okay.
Mm-hmm.
For
Mm-hmm.
academia, you use a XOR based distance metric, which determines which is the closest network where you can store this. So when uh, when a new node joins, if you assign a new unique identifier, and you will give some part of the hash table to this new node, and if that node gives or it gets failed, then this portion of the hash space is again redistributed to other nodes. So
Okay.
the DHTs distribute this data across multiple nodes with the use of the hash function, and it will have some structural approach on how this data should be distributed to other nodes in case of a failure or in case of a node leaving, based on the algorithm that it will have on how the DHT algorithm, how the data should be redistributed. It will take care of the redistribution.
Okay.
But this is not central. It is distributed.
Okay. Okay. Addition and removal of a node, does that kind of disturb the cluster that way? Because redistribution may be a heavy activity, right? So addition of a node, if that particular node addition is going to disrupt the entire existing nodes in order to shuffle the data across, then wouldn't that be
Hmm.
a problematic part?
It will lead to a bit of extra work, yes, but it will be much better or much lesser than replacing a master node, because only some portion of the data will be redistributed, right? Not the whole one. A very small part of, if you imagine uh, thousands of nodes connected, only one node fails, the amount of data that node carry which needs to be distributed will be very less.
Okay, okay, that way. Yep. And then there will be there is a need for a mechanism which is going to kind of do the distribution that way then, right?
Hmm.
So there would be some sort of disturbance when a node is added or removed, but that's kind of minimal is what you're trying to come at,
Yes, yes,
as against the master slave architecture. I mean, master becomes the most significant point of failure, and that's going to bring down system. Here, system will not be brought down, but there will be a
hmm,
disturbance, and that ring will need to settle down after addition or removal of the node. So that is something
yeah.
which we'll need to be cognizant about.
So also because of the depending on which algorithm you are using for this DHT, the node may have its own data, and it will also have neighbors information. Like,
Hmm.
yeah, so some, like, how this neighbor is contributing to this DHT, your node will know. So if the neighbor fails, then this node will have some information based on which the data can be retrieved.
Okay. Okay. And then replication also will help you, right? Because every node is
Yes,
kind of replicated at another place also.
yes, it's better to replication is very critical in B2B. Important.
Okay. Thanks.
So key components of a P2P system is uh, peer nodes, which are the heart of the system. That is, each will act as both client and a server. It will share resources and participate in the communication. The overlay network, which is the logical layer that connects these peers and enables them to exchange data efficiently, regardless of the underlying physical network. You need an indexing mechanism that we just discussed to organize and locate shared resources. Without indexing, we cannot find data in a large network. And if we do not have a indexing, then it would be like searching for a needle in a haystack. So finally, bootstrapping mechanism is where we allow processes that allow new nodes to discover in the existing peers and join the network without much issue. So these all these components form the foundation of all P2P systems. It could be pure, hybrid, structured, unstructured. We need all these four. All these four things are very critical components of a B2B system. So coming back to the question just we just discussed in detail, why we need hashing in P2P system? We have many nodes storing and sharing data. A major challenge is where do we store a particular piece of data and how do we find it quickly? And hashing is the one who helps us solve this. It's a mathematical function which will take an input like a file name or a key, and it will output a fixed size value. This value to then decide which node should store this data. So the beauty of using hashing is that it distributes data evenly across nodes. It also supports fast lookup. Both of these are very essential when dealing with thousands or millions of peers. And as the scalability of the system increases and nodes join or leave. So the simplest technique is modulo based hashing, where we take the hash key and compute, you know, uh, modulo where this n is a node ID. For example, if we have 10 nodes and the hash of file is let's say 23, we'll do 23 mod 10, which will give you 3. So the data will go to the node 3. This is quite straightforward and works well for a static network, but there is a big problem. What is the problem? This works for the static network, but there is a problem. When a
Addition
new
and
node
removal of
joins,
node.
yeah.
Addition
Mhm.
or removal of the node is going to change the hash key value.
Yes. When a new node joins or an existing node leaves, the value of n will change, and almost all the data needs to be remapped. This makes the simple hashing unsuitable for dynamic and very large P2 scale P2P systems. So I think let us take a 5 minute break before we continue our discussion on the other approach of hashing. So we can restart around 9:20 because it's a theory heavy kind of a class. Let's take a break now. so let us continue. So we saw that simple hashing has a problem. This is straightforward, can work for static networks, which will not change, it will remain fixed. But if it is a dynamic network that is nodes come and go, in that case, it's a big problem because if a new node joins or an existing node leaves, the value of n will change, and almost all the data will have to be remapped. And this will be an issue when it comes to having a scalable system. So this simple hashing is unsuitable for any dynamic or large scale P2P system. So how do you overcome this problem of which is caused by massive data shuffle? So to overcome the limitation of simple hashing, we have something known as consistent hashing. And it is usually the standard approach which is being used in large scale distributed systems today. So instead of assigning data directly using a modulo, what we do is we imagine a circular hash space, which is called a hash ring. Both nodes and data are hashed into this space. So each piece of data is stored on the first node clockwise from its position on the ring. We'll see an example. Now, if a node joins or leaves, only the data in its immediate neighborhood needs to be moved, not the entire data set. This helps to make consistent hashing very highly reliable, highly scalable, and fault tolerant. And hence, it is used in real-world systems like Amazon Dynamo, Apache, Cassandra, even Code. So, how this works? Let's see with an example. So, assume a hash space from 0 to 99. For simplicity, these are the numbers we chose. We have three nodes. Node A has hash 10, node B has hash of 50, and node C has a hash of 80. This is the first step, hash the nodes and place them on a ring. So how this ring will look? So it might look like he is here, his hash is 10, next is B, his hash is 15, then we have a C. C's hash is 80. And this forms a ring. Okay. Now, next step is hash the keys and place them. Now, suppose we have four data items 12, 30, 60, and 90. How you will place them? First hash is 12. So 12 cannot come here. It is greater than 10, so it will be here. Next one is 30. Again, 30 cannot be here. 30 has to go to B node, greater than 10. So 12 and 30 will be here. Next is 60. 60 cannot be on B node because it's greater than 50. It will go here. The next one, data item was 90. 90 cannot be here because it's greater than 80 and it's a ring network, so it will go here. Is this example clear? Okay.
Ma'am, you said clockwise, but probably we saw counterclockwise
Oh,
arrangement
sorry.
here.
Oh, sorry. Okay, maybe I correct. I drew this. I should have drawn it. My bad. I think my so yes, you are right. So uh, we will have uh, I had drawn 10 here. So counterclockwise, which will be the first node. So we can have 80 first, then there will be 50, sorry, then there will be 10. Then this is correct. Yeah,
Yeah, yeah.
only the placement of nodes. Yes, you're right.
Yeah, 10, 50, 80 will also do. As long as we
Hmm.
are moving in clockwise direction, we are good.
Yes, yeah, okay, yes. We should have the direction method. So as long as, yeah, the direction
Yeah,
is correctly placed, it is fine.
yeah.
So now what happens if you have a new node D and its hash is 70? In that case, it will again get placed. Here we had 80, here we had 50, so 10. So it will get placed somewhere here.
Again, the direction is
And
not correct, ma'am. It should be other way around.
now this, yeah, anti-clockwise direction. So in this case, in this table, what will change? Only
Now, 60 will need to go
hash
to
is,
D70
yeah,
node.
yes.
Ear- Earlier it was going to C80. Now it will go to
Hmm.
D70.
This will go to D70. Okay. Now, even with consistent hashing, some nodes might still end up with uneven loads. So there is another solution which is virtual nodes. So instead of representing each physical node once on the ring, we place it in multiple positions. For example, node A could appear as A1, A2, A3 in different points. This helps to distribute the load more evenly and it also allows flexible rebalancing when there are nodes joining or leaving. So it's especially useful when nodes have different storage or processing capabilities to have this virtual nodes. So where consistent hashing is being used in code, which uses consistent hashing to efficiently locate data in the fully decentralized network. Amazon Dynamo and Cassandra are virtual. They use virtual nodes on top of consistent hashing to support massive scale and handle frequent node down. This uh, This extra hashing layer is what will helps you, helps our P2P and distributed storage systems to be both scalable and reliable. So next is before we talk about how we can know add nodes, uh,
Yeah, ma'am, one
how do you
question.
know add nodes?
One
Yeah.
question on earlier slide.
Mm.
Let's go back some more slide where we added the D70. Oh yeah,
Yes.
just hold here, or rather, just go back maybe a couple of slides earlier. We had key 60 earlier. Okay. Now, when we kind of set up the cluster of three nodes to start off with,
Mhm.
key 3, which has hash value of 60, will be stored on C node, C80, right?
Yes. Yes.
Uh, if you go ahead now, wherein we have added a new node,
Mm.
D70, which sits between B and C. So next
Mm.
time on the next screen, next slide. Yeah. Now here, key 60, key 3, which hash value
Mm.
60 is going to sit on node D because that's the closest in the clockwise direction.
Mm.
Now we already had that hash value 60 stored on node C earlier. Now
Mm.
we are storing it
Mm.
on node D, which is 70.
Mm.
What
Mhm.
happens with the value which we have already stored on node C in this setup?
Okay. Um, yes. So when you add a new node, what
Mhm.
happens is you have to you will have to move this data from the existing node to the new node, and this this uh, so you what you do is data that falls within this node's range will have to be moved to this new node, and then you have to update your routing table. So the routing table will be updated of the neighboring nodes to reflect this new node is created, and now you redistribute the data, and you then delete the data once the routing, rerouting, and data movement is done. Then you remove the data from the data of your node, the earlier node, that is C of it was on C of 18. Na? You remove it.
Okay, okay.
Suppose
So
your
that
node,
way,
yeah.
mhm, mhm. So what you're trying to
So suppose
effectively comment is between node B and C, as in range 50 to 80, whatever keys were there, those were stored on node C earlier. Now, because of introduction of D node, which with hash value of 70, the keys between 50 to 70 will be stored on D, while keys between 70 and 80 will be stored on C. 71 and 80 effectively. So
yes,
that particular distribution will need to be done whenever a new node D is inserted between B and C, is what you're trying to comment, correct?
yes, yes,
Okay, so that is the cost which we have to pay whenever a new node is added, effectively, right?
yeah,
So that's
yes,
rebalancing which we are trying to come at.
yes,
Okay, how does this happen in reality? As in, see, it's dynamic, right? So a node gets added and removed every now and then in a bigger system. How it is managed? As in, is there some software or is there any automated mechanism which kind of takes care of this? How it happens in the reality? Because it's a task, right? It's a legitimate complex task which needs to be taken care. So how
yes.
it happens
So
in reality?
yeah, so you have some you do have some DHT applications, uh, like you know uh, you have this BitTorrent DHT library, which implements this, which is available on GitHub also, I think. Then you have also uh, in for especially with for torrent you have many these open source libraries that you have. There's another library which is on get right. So You have uh, you have open source libraries, and these, especially these people like Amazon and all, will have their own library developed for their particular system with the algorithm that they choose to use for, or the algorithm that they choose to use for in case of PDF. Because as you just said, when we add a new node, there are some decisions that you need to take, whether you have to immediately delete this data which was on the earlier node, or you retain it for a certain period and then do it. So these things are will be specific to the organization or the system that is trying to develop it. So well, there are open source implementations of this. You There are implementations of DHT for each organization based on their requirements. Mm,
Okay,
So
okay,
as
that
I've
helps.
mentioned, yeah, as I've mentioned, CORD multiple times. CORD is also a popular DHT algorithm, and it uses a ring structure to map nodes to hash keys. You can check it out. Even the
Got it.
Academia and Pastry that I've mentioned, they are DHT algorithms, which, as I mentioned, Academia uses XOR-based distance matrix, whereas Pastry uses prefix-based routing. So there are multiple such DHT algorithms.
Right, and then when this particular node gets added and removed in a way, because
Yeah.
of this particular
Yes.
rebalancing, there will be a certain time period for which we are not really sure about where the data lies, right? Now, in this
Not
particular example,
necessary.
not
Not
necessary. Okay.
necessary. That has to be clearly, that will be built in the algorithm. That
Hmm.
once the data is moved, you the uh, the location of the data, obviously the it will get updated. Also, it will not be immediately removed from the system, the earlier node, to ensure that there is consistency in the data, so that everything is taken care of by the algorithm. There will not be any unsurety. There will be clarity, be- and that clarity is designed in the algorithm,
Okay.
where to
Okay.
expect the data to be. Hmm.
Okay. Okay. In this particular example, whenever there is a movement from C to D, there would be a transit time wherein
Yeah.
some data will migrate from one place to another, right? And if
Hmm.
since it is a live system, right? If the request comes
Hmm.
in for exact same data
Hmm.
which is in transit, then that's going to be
That,
a
that,
problem.
that, that time, no, that time the request will go to C node. Till D has confirmed it has received data, it is consistent and is ready to function, the request will be taken care of by C node.
Okay, okay, okay. So for transit time, C is going to be
Yeah,
the node which is going
functional.
to serve the request. So
Hmm.
until entire data is moved on to D node in this particular case, C is
Hmm.
going to retain all the information which is going to be moved effectively on node D. So until node D
Yes.
settles, C will hold the data. And
Hmm.
once everything
Yes.
is settled, C is going to take off those keys which are present
Hmm.
on D node now. Okay.
Yes.
Okay.
Yes.
That helps. Yeah.
Yes. So, yeah. So these are the real world hashing or DHT implementations which you can check out. And there are some open source also implementations available on GitHub. You can check those out as well. So moving back to now, what is scale out architecture and how do we now proceed with this? Uh, we already discussed what a scale out architecture is, but we did not discuss what scale out against or versus what a scale up is. So scale out is horizontal scaling, which is what is behind most large distributed systems, where you do not upgrade a single powerful server, but you add more nodes to the system. Each new node will contribute its additional compute, storage, or network capacity. The system will grow as a whole and with each addition. This approach is more flexible, cost effective, fault tolerant, and that's why we kind of go for scale out. But and so P2P systems that we've seen so far are heavily relying on scale out rather than any vertical scale. Whereas scale up is basically improving the performance or upgrading one machine, adding more CPU cores, maybe more RAM, extra storage. It is powerful, but it is expensive and limited. Scale out increases capacity by adding more nodes. Each node might be less powerful individually, but together they deliver far greater scalability and resilience. And the choice between the two depends on what kind of a workload you have, what is the need of this growth. But in large scale systems, scale out almost always wins over scale up. And scale out is hence used in cloud platforms, P2P systems, and even distributed storages. So one of the biggest advantage of scale out system is elasticity. That is the ability to add nodes when the system is running without any downtime. So when a node joins, it needs to discover and join the cluster, usually via bootstrapping or gossip protocol. It receives part of the workload of data, which is using hashing based on the distribution of portion we just discussed, and any partition migration that we need to do of the data. It has to then update the metadata or routing tables. So all players will know how to reach it. So this is how cloud platforms automatically scale your service when traffic spikes, or even how Cassandra expands storage just by adding a new server. So nodes can also be removed, as we just discussed, either intentionally or it could be due to a failure. In a planned removal, the system redistributes the departing nodes data to others, and it will update the routing information as we just discussed. In case of failure, nodes will use heartbeats or gossip to detect the failure, and it will trigger recovery actions like replication or re-election of leader, which also we discussed in earlier slides. In both cases, the goal is same: no data loss, minimal disruption, and continuous service availability. This is all these three are very important, and these are the key parts where we can get a fault tolerant design. So while scale out is powerful, there are challenges that some of them Yuvraj mentioned. Data redistribution, it has to be handled carefully to avoid any bottlenecks. Load balancing has to be ensured so that no node is overloaded while others are idle. State consistency, that is, it is crucial that every node knows the current topology. And finally, we must minimize the performance overhead. It is during these transitions, the system should remain responsive even as nodes are joining or leaving. We should not be in a state that we just discussed that a new node is added, so the data that is be shifted to that node is not available. Should not be the case. Should be available on the earlier system till the new node joins and stabilizes, and then takes over the task of giving data for that particular file. So how do we ensure all this? So the key to
Ma'am, sorry.
ensuring this,
Sorry
yeah,
to interrupt. Question on
yeah,
earlier slide.
yes,
Maybe one more. Couple of slide earlier.
yes,
One more.
hmm?
Now, see, no, no, no. The next slide. Yeah. Elasticity scale out.
Okay,
No, no, no. The one where you talked about removal of the node as in the failed node. One
okay,
more I had. Yeah, just hold here. Now we talked about situation when a new node is added or there would be
yeah,
a planned removal. So those are intentional activities. wherein we know
yes,
that we are doing something consciously, so I need to do a redistribution of information. But when
yes,
a node suddenly goes down, as in a failure use case, we don't
hmm,
have prior information that node is going to fail, right? In a way, it fails
hmm,
and then we know that it has failed.
hmm,
So it's kind of reactive. It's not proactive step, it's a reactive step. And then when that node goes down, it is going to take out some information with that particular node, right? So what how that information is kind of retracted or how that information is served by other nodes then, if it is not with them.
yes.
Was
That's
my
what we are
question clear
discussing.
enough?
Yes, yes, yes. That's what we are discussing in the
Okay.
next slides. So
Okay,
I'll
okay,
move to
fine.
next slide. If it is not clear, we will
Sure, sure, sure,
rediscuss.
sure, sure.
So,
Okay.
so in any large distributed system, failures are not an exception. They will happen, and they are the norm, right? So machines crash, disks fail, networks go down. We cannot prevent all the failures, but we must design the systems to tolerate these failures. So that's why redundancy comes in. By storing multiple copies of data or having backup nodes ready to take over, we can ensure that the system stays available, services remain reliable, and data is not lost even if something fails. So essentially, redundancy is needed, and it's about building the resilience that we need in this system, and it has to be done from the start so that we do not lose the crucial data. So, what kind of redundancy? So, the answer to your question, Yuvraj, is having redundancy in this network. Okay, that's
Yep,
how we manage the fault tolerance. But what kind of
yep,
redundancy we should have, we will discuss in the next slide. So, there are two major ways of how you can have redundancy. Node redundancy is where we have standby nodes or multiple active nodes. So, if one fails, other continues the work or quickly takes over. This is common in load balanced web services or replicated compute nodes. We can have data redundancy where we keep the multiple copies of the same data across different nodes or racks. Even if one copy is lost due to some failure, we can still recover from the other copy. Obviously, how to choose between the two is the trade off. More redundancy improves reliability but also increases storage cost and sometimes update overhead. So the design of your system must balance these factors as well. That is the increasing cost and increasing storage and update overhead. This is also important because that if you have multiple copies of data and if this, let's say a variable A of the file, some file is changed, you need to update this variable A in those all these multiple copies as well. So this adds extra overhead. Okay. So for that, that is where what is the replication strategy matters. So there are multiple types of replication strategies, and depending on algorithm that we use, they will choose one. So first one is full replication. So every node stores a complete copy of their data, entire data set. This is highly reliable. It is even if many nodes fail, data is still available. You get very fast reads. Data can be served from any node. But what is the disadvantage? It is expensive, requires a lot of storage and bandwidth, and updates also are very costly because every change must be propagated to every node. Where you can use this? It could be a small data set or a system where reliability is most important than storage cost. Only in that scenario you can use this. There is no one solution to all. So depending on the requirement of your system, you'll have to choose between these replication strategies. Then you have a partial replication. So each data item is replicated on only on a subset of nodes. Advantage balances reliability with lower storage cost, easier to scale. Not every node needs to store everything, but there are disadvantages. If there are very few replicas, then only by chance those nodes only fail, the data can be lost. So locating the correct replica may also take longer. Now, the use case could be you can have a large scale system where full replication is just not possible. In most large scale systems, it's not the case. You can use a partial replication. Then you have a quorum based replication where you have read or write operations succeed if they reach a majority of the replicas. So uh, now an example could be where you can have a n, which is total number of replicas. W you can have where minimum number of replicas thus that must acknowledge or write, and R is minimum number of replicas that must respond to a read. So what does this mean is if you have a quorum based application, you create you formulate what should be considered a valid data with a with some kind of a function. So a condition could be that W plus R is greater than N. So if you have three replicas, okay, you have three replicas and you have two write replicas and two read replicas. W and R are minimum write and minimum read replicas. So, and if your formula W plus R should be greater than N, this ensures that at least one replica involved in any read has the latest write. So this, you know, guarantees the consistency. So, for example, if a dynamo for Amazon, there n is equal to 3. So each data item has 3 replicas. W is equal to 2. Means write must be confirmed by at least 2 replicas. Read is 2. So read must get data from at least 2 replicas. So this kind of gives the balance between availability, consistency, and fault tolerance. Is this clear? This dynamo example that you have to ensure that if there is a node failure, at least 2 replicas should have the updated write value, or 2 replicas should have updated read value, and the maximum number of replicas for every data is 3. Okay. So in summary, good replication will need maximum gives you maximum reliability, but again maximum cost as well. Partial replication will is a trade-off. It may be between cost and reliability. Forum based is flexible. It is tunable between both consistency, availability, and performance. So now redundancy is effective only if the system can detect failures quickly and respond intelligently. So how do you do the detection and how do you handle such scenarios? Systems often use heartbeats that you I think discussed in the first uh, initial classes or gossip protocols to detect if there are any dead nodes. Once you detect, they read out the task to other healthy nodes, and this is called as atomic failover. This may also uh, need re-replicate data, that is, to restore the desired application data. If the fault, if the failed node was a leader or coordinator, the system will have to elect a new leader. That needs to be done automatically as well. All these mechanisms have to work together to ensure that if there is a failure, it should not bring down your system. So one uh, crucial tool for failure handling is called checkpointing. This means you periodically save the current state of the system so that if any failure occurs, we don't have to start over. We can resume from the last checkpoint. So for that, you can have a coordinated checkpointing, which is all process checkpoint together to ensure there is a consistent state. Or you can have an uncoordinated checkpointing where each process checkpoints independently. This is faster because there is not much coordination, but the recovery might be a bit complex because it's not coordinated. You can have an incremental checkpointing as well, where only changes since the last checkpoint are saved. In that case, what happens? You end up saving storage and time instead of checkpointing everything. So these checkpointing techniques are used for high performance computing system, large scale distributed trainings, and even distributed databases. It's a very important, important technique to ensure that we periodically save the current state of the system. So even if failure occurs, we can we don't have to restart. We can start from the point that we have saved the checkpointed point. So uh, now this redundancy and checkpointing are used in many large scale systems. So HDFS keeps three replicas of every data block to survive multiple failures. Cassandra uses quorum replication, and it also hints on uh, using uh, consistency model as well as I think availability. Kubernetes automatically reschedules failed containers to healthy nodes, and in many HPC, MPI jobs also use checkpointer restarter to avoid any losing of whatever computations had happened so far. So uh, with this, we can conclude that redundancy and recovery mechanisms are very essential and are very important building blocks for any reliable distributed system. Is this clear? Okay. With this, if there are no any doubts, I would like to stop today, and we will uh, learn a few more things about P2P systems and distributed systems, and then learn about MapReduce, which is a scale-out P2P distributed system. We will That will be a case study of the MapReduce architecture and how that uses all these different features and characteristics of P2P systems. So you all answered, Mitchell? It's done or Okay, answering next semester, week, sorry.
Next week classes wouldn't be there, ma'am, right?
Yeah, yeah. You answered last week or you're yet to answer?
Sorry, that was not
The,
clear to me.
you answered midterm last week or you are going to answer
Okay,
next
I'll
week?
be doing it next time,
Okay,
next week.
okay,
Yeah. Thank you, ma'am.
okay. All the best then. Yeah.
Yes, thank you, ma'am.
So, ma'am, who were answered last week, and
Mhm.
there are few left with they are going to attend this week. All the
Yeah.
evaluation is going to happen after the next week, or evaluation is going on?
No, I think evaluation has already started for last week.
Okay.
Yeah. At least as far as I know, I've provided them the answers and the the instructor is has started evaluation.
Okay.
I do not know the exact updates, but she has started. So
Ma'am, when will we
yes,
get the results of midsem? Ma'am?
you should get it by if you have answered last week, then maybe by this week or next week you'll get within 1 or 2 weeks.
Oh, okay.
Yeah.
Are we
Ma'am,
going to
one
get
request, ma'am. Ma'am, will you show us one program like execution in the lab?
Uh, okay. So which one you want to see specifically? Is it like MPI you are referring to, or
Ma'am, anything based on your comfort.
no? See, OpenMP. Anyways, I've shown the OpenMP, MPI as well as P-threads. I've shown them in on my system during the class. But labs, I still do not have the access to virtual labs. Maybe I'll send a mail again today. I'm told that you have access to any other lab.
Actually, I
Did
tried
you get access?
accessing, but it is taking lot of time to launch. It's taking
Okay.
very long to launch.
So this lab is available to you for this course at only or some other course you are referring to?
This course is also there, ma'am. I just tried to launch one of them, but to allocate EC2 itself, it is taking so long.
Okay.
Yeah,
I'm
So
not sure
yeah.
if my network had issue or others are able to access. I'm not sure.
So has anyone else tried? Has anyone else tried? Okay. Let me check, and uh I will send a mail again today.
Yeah, I'll try today. But I
Okay.
think that allocation of those resources actually require huge internet. I've seen that.
Okay.
Hmm. Okay.
Okay.
Ma'am, if you can
Fine.
take
I
up
will.
example for each, as in pthread, OpenMP, and MPI, real life
No, P-thread we
problem.
have
I mean,
already.
we
So that's
saw.
why what I've done is, as I mentioned, I've uploaded the questions that we did in our campus on-campus lab. I have uploaded that. I will also maybe upload the for OpenMP and MPI. I have uploaded both the lab document that we give to students, which they are expected to prepare, and the question. Okay. For both OpenMP and MP I have uploaded. I'll also upload the assignment problem that I recently given on campus, which is using OpenMP for a real life problem. Okay, you can go through that,
Okay,
and I'll see how I can show you the solution. Uh, and I will check with the lab also. With lab also, I'll write them right now again. I'll check file.
okay, you have posted that on Takshila, right? Is what you mean?
Yes, 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 yes. I've already posted that.
Okay, okay. Let me check that out. Yeah, thanks.
Okay, I'll upload the assignment problem of OpenMP as well, which was also an interesting problem.
Yeah, that will help. Yes.
Mm, If you, I'll give you some time to try it out. If you really need a solution from me, then I can provide you. But
Right.
I want you all to try
Example.
it out first.
Right. Example codes and practice problems. Those are the two sections, right? Where you have
Yeah,
them.
yeah. Yes,
Okay.
example codes are what I covered in the class.
Okay.
The ones that we did in the class, and
Hmm.
practice problems are the lab problems or the assignment problems.
Okay. Okay. Fine. Thanks.
Mhm. Yes,
Ma'am, can you also please stop the recording before you exit from the meeting?
yes, I'll do that right now.